Okay, so I know it's a lot of me talking, and I know a lot of notes going through this, and hopefully this is making sense. And I'd rather give you of examples and you kind of looking through and trying them on your own, and or watching the video and then checking your answers as well. But it's a very important concept, this area that we bound between two curves. And remember, from the first two videos, you could know you could be bounding right to left, and that would be in terms of y, or you're bounding top to bottom, and that could be in terms of x. Now, look at this. How exciting. We get trig and no picture, and we have to evaluate this region. So isn't this just lovely? So hopefully, and again, on the AP exam, they sort of you expect to know a little bit about trig, that you remember your sine function. So your sine function looks something like this, right? And then your cosine function, oops, that's going to be too thick. There we go. Your cosine function starts at 1 and does one of these things. It just chases your sine graph. Okay, so it says find the area of the region bound by the curve sine x, cosine x equals 0, and x equals pi over 2. So x equals 0 is a vertical line. X equals pi over 2 is another vertical line, which is right here. So I need to look at where do the graphs intersect and what bounds these regions by those 3, or actually 4 particular equations. And so there's actually 2 regions. If you see this, I'm trying to highlight it. There's this almost triangular shape here, bound on the left by that vertical line, bound on the bottom by our sine function, bound on the top by cosine. And then over here, I'll do a different color to start with. Like here, the top now becomes the sine, the bottom is cosine, and this time the right boundary is pi over 2. Now, the thing I want to think about is like, well, when do these functions equal each other? When does the sine and the cosine graph equal? You could set it up as an equation, like when does sine of x equal cosine of x? Maybe divide over the cosine so you get the function tangent, and you get x equals 1. And then you also might think of your unit circle days and thinking about, right here, halfway between 0 and pi over 2 is where the sine and cosine functions equal each other. Same place where tangent is 1, right? That's a 45-degree angle when x is equal to pi fourths. And the reason that's important is because at that instant, at pi fourths, that's when the 2 functions change. So if I'm going to set this up as 2 separate integrals, the first integral would be between 0 and pi fourths. The top function is actually the cosine function, and the bottom function is the sine function. And then once I realize that they switch from pi over 4 to pi over 2, the top function is now the sine function, and the bottom function is cosine. So I could set it up as 2 separate integrals, but then I'm going to, I might want to say, well, wait a minute, they're the exact same area. So if I find one of them, just double. And it doesn't really matter which one you find, but I like this one a lot better, simply because there's a bound of 0. It just makes the calculation that much easier. So that's what I'm going to do. I'm going to evaluate that first one. I don't know, maybe go to this one, purple. So I'm going to integrate from 0 just to pi over 4 of the cosine function minus the sine function. Okay, now be careful. We're doing antiderivatives, not derivatives. The antiderivative of cosine is positive sine. Antiderivative of sine is negative cosine, but there's already a negative there. So that's actually going to become a positive value from 0 to pi fourths. So that's sine of x plus cosine of x when evaluated from 0 to pi fourths. So we can put this in and we get sine of pi fourths plus cosine of pi fourths minus, now just because this is a 0 doesn't mean this whole thing is 0, so be really careful. because I know that one of these two values, cosine, like sine or cosine of 0, is going to actually give us something, and it's actually cosine of 0. Cosine of 0 on the unit circle, cosine of 0 is 1. So I need to make sure I remember that. Sine of pi fourths and cosine of pi fourths. And again, if you're not remembering your right triangle trig, 45-degree angles, 1, 1, root 2. And so the sine and cosine would both be 1 over root 2 or root 2 over 2. Simplified. So root 2 over 2 plus root 2 over 2 minus, and then this is sine of 0, which is 0. Cosine of 0 is 1. So root 2 over 2 plus root 2 over 2 is 2 root 2 over 2, which is just root 2 minus 1. And so that is the area of just one region. I have to remember to double that so that I get both. So that's actually 2 root 2 minus 2. Excellent. Okay, now example 7 and example 8, I've actually already worked out. So I'm going to ask you maybe to pause the video and try them, and then unpause the video. And what I'll do is I'll show you my solution and kind of just maybe emphasize and talk about some key points. Okay, so 3, 2, 1, here we go. So I'm noticing in this example a couple of things. One, it's x in terms of y, and that does in my head, I need to remember that I'm going to have to be in terms of y as I go right minus left. Okay. The other thing I noticed is they didn't give me a picture, so I'm going to try to figure out which one is to the right and which one is to the left. Now these are both parabolas, and so in red I've highlighted or boxed around and graphed red over here on my actual graph. That one is opening to the right. This blue one is opening to the left. But again, how did I know which one was farther to the right? Well, I just picked a value in between 0 and 3. So I set them equal to each other, figured out y was 0 the lower bound, 3 was the upper bound. Great. So then maybe let's just see who's farther to the right when y is 1. When you put 1 as a y value in that first function, 1 minus 4 times 1, so 1 minus 4 is negative 3. When I put 1 into this function, 1 squared is 1, but still make it negative, plus 2 is 1. So between the two, 1 has an x value that's farther to the right than this one. So I now know that the blue graph is to the right of the red graph, and that allows me to do right minus left. So I just want to emphasize that that's how I knew that it was the right side minus the left side. Did the antiderivative and got a value of 9. And again, you should work this out. No, don't just copy it down, but kind of make sure you can actually also do the calculus. Okay, and then the second one, I like that one, the next example, conceptually, because we're not even finding an area. We're just thinking about it from a conceptual point of view. And if it says like, but do not solve, that's kind of a common set of directions, believe it or not, on the AP exam, because they don't necessarily they obviously want you to know how to do an antiderivative, but they also want you to know the concept of how we measure this displacement. So when I'm measuring it in terms of x, which is my first one, I'm thinking top minus bottom. The top function, which is this curve, and the bottom function, which is this line, y equals 1. So that's where the bottom function came in. The top function was log base 2 of x. And both of these bounds must be the x components. So at this point here and at this point here, notice that I chose the x coordinate of 2 and 8. So 2 and 8. When I'm going right to left, I'm going to actually choose the y component. Oops, there it is. The y component of 1. Oh, that doesn't really help because it's green. And 3. So 1 and 3. And then again, doing right minus left. Put a pen here. So the right minus the left right side minus left side. What's the boundary over here? It's x equals 8. And what's the boundary here? Well, I can't call it log base 2 of x anymore because I need it in terms of y. So how did I get this 2 to the y? Well, if log base 2 of x is equal to y, I just did an algebra 2 exercise where I can rewrite this. 2 to the y is equal to x. 2 to the y is equal to x. These are interchangeable. So when I want things in terms of y, then I need that piece right there. Whether you evaluate the first integral or the second integral, both of them will give you the same value because you're representing the displacement between these two curves or three curves, in terms of the region R. Okay, so all of those examples, again, lots and lots of examples, and I'm trying to give you like little hints and tips between that should prepare you for that homework. So go through setting them up, and that's just as important as getting to the right answer. If you get stuck, go back, rewind, look at a couple of examples, try them again. But that's a big concept and application of finding area between two curves. Okay, so